Today we are going to study about electric field, how to find due to charged spherical metal shell. This is a charged spherical metal shell. Shell means inside vacuum. It is made of metal, spherical shape with radius r. It is charged to Q. Now it will establish electric field around it. Here at three different situations we have to find inside how much electric field, on the surface how much, and at exterior point how much electric field we have to study. And here total charge it has got is Q, which is equal to 4 pi r square area into charge density. Surface charge density is sigma. Area is surface area is a spherical surface is 4 pi r square. So area into charge density is total charge. Next, first we are finding here electric field at exterior point. This is a charger shell and this is a exterior point, outside point, which is a distance smaller from center. Here smaller is greater because smaller is the distance of the point at where we are finding electric field, and bigger is the radius of the charger shell material. So smaller is greater. Now to find electric field at point P, first we can imagine that electric field would be radially away. Symmetrically we can imagine like this. Why radially in outward direction it points? Because this is a positively charged body. We know in case of positively charged body, field is away from the body. That means what? It should be radially away, the direction of electric field intensity. Which one we are going to find now? Direction of electric field is radially away. Magnitude we are going to find. And elemental area ds I am showing here. That elemental area direction is perpendicular to ds, means one radially outward only, inside to outside only. Always elemental area's direction is defined as inside to outside. In that way, the area direction, which area? Not complete area. The elemental area ds which we have chosen here, that elemental area and electric field both are in same direction. Now at first d phi will write. D phi is what? Flux associated with this elemental area. Now according to formula, flux associated with elemental area is d phi is equal to E bar dot ds bar. Now if you expand this one, E ds cos theta. Theta means angle between E bar and ds bar. Both are in same direction. Angle is between them is 0. That is why it become cos 0. We have to write here. Cos 0 is 1. So d phi is become EDS. Now this after finding elemental the flux through elemental area ds, then if you integrate this, you will get total flux diverging from the complete Gaussian surface. That's why phi total flux is equal to integral d phi. That is integral EDS, because d phi value we got here EDS. Integral EDS. Then E will remain constant here. Constant means in magnitude. Here Gaussian surface point, which is at distance smaller. So here also electric field should be E. Here this point is also at smaller distance. So there also electric field should be E, because on the Gaussian surface every point from the center at equal distance. So at every point electric field should be same. In that way electric field magnitude में constant था. So integration से बाहर आ गया. The integration is acting on ds, means what? Total of ds areas. So such ds areas, if you imagine add integration is what? Addition of all ds areas. So all ds areas if you add complete Gaussian surface area you will get. So integral ds value will be for total Gaussian surface area. So that's why phi is equal to E into total Gaussian surface area 4 pi r square, because Gaussian surface is in spherical shape with radius small r. So its integral ds is total area, that is 4 pi r square. So in that way flux answer is E into 4 pi r square. We got this is equation 1. Now equation 2 how to get. This is what same flux we are finding by using Gauss law. In the Gauss law, what is that we need? Total flux is given directly is given by 1 by epsilon 0 times of total charge. Total charge where which total charge inside the Gaussian surface. Here Gaussian surface is bigger one with smaller radius, and a charger shell is inner one. So that means what? Gaussian surface consists of complete shell. So Gaussian surface के अंदर complete शेल के ऊपर जितना पूरा चार्ज है वो सब Gaussian surface के अंदर का चार्ज माना जाता है. So here we need the charge present inside the Gaussian surface node, the charge present on the spherical shell. So that's why flux is equal to 1 by epsilon 0 into total charge which is present inside the Gaussian surface. That is inside the Gaussian surface complete shell is there. So complete shell पर charge लिखना पड़ेगा. So in that way flux answer we got again as 1 by epsilon 0 Q into Q. This is according to Gauss law. So from equation 1 and equation 2 we are getting E is equal to, if we equate both flux answers, we get E is equal to 1 by 4 by epsilon 0 Q by R square. And so in that way relative field intensity we got at R distance. This answer of relative field intensity due to charged shell we can express in the density formula also, because you know total charge can be expressed as 4 by R square area of the shell into charge density sigma. Then if you put here, then 4 by 4 will get cancelled. So answer for relative field intensity is sigma R square by divided by epsilon 0 R square. In that way another answer can be written in this another form also. But anyhow, what we are understanding, E is proportional to 1 by R square. Just like this is the answer, okay. Just like in case of point charge, if the charge is present at point at R distance, how much field relative field intensity we got? We know 1 by 4 by epsilon 0 Q divided by R square. Same answer we got here. Same answer due to shell also we got. That means what? The charge which is spread on the spherical shell is behaving as if it is at the center and it is a point charge. Because in case of point charge also at R distance relative field intensity is same formula. Now also we got the same formula in case of shell also. That means what? The charge present on the shell is acting as if it is at the center and a point charge while creating electric field at outside. Because this outside only we found. Next, electric field we have to find on the surface. When we are finding electric field on the surface, again we have to imagine Gaussian surface just covering the shell, because we are going to find on the surface itself. So our radius, Gaussian surface radius and shell radius are both coinciding, big R. Now again we have to take ds area on the Gaussian surface, that is on the shell, and through ds area the flux is E bar dot ds. Total flux will be integral E bar dot ds. Then integral EDS cos 0. Because here angle is the same, angle is 0 because electric field is radially away because positive charged body, and ds bar direction is always inside to outside. In that way direction ds bar, this ds bar and electric field both are in radially away, which one both are in same direction. So angle between them is 0. So here in the place of E bar dot ds bar, because of scalar product we are getting EDS cos theta. In the place of theta we have to put 0 angle because E bar and ds bar in same direction. Then cos 0 become 1, then integral it become EDS, so E is taken out, E into integral ds. Here integral ds means what? Total Gaussian surface area, and Gaussian surface is coincident with shell surface we have to take. So E into 4 pi big R square. This is the flux we found geometrically. Now flux by Gauss law, it is 1 by epsilon 0 times of total charge. So Gaussian surface is consisting of complete shell. That's why shell complete charge. This is equation 2. This is equation 1. So if we equate both the flux answers, phi is equal to, then we got E into 4 pi R square is equal to 1 by epsilon 0 into Q. So this is a flux, total flux. I got geometrically we got this is a total flux by Gauss law. Both flux answers we have to equate. Then from that E is equal to 1 by 4 pi epsilon 0 Q by R square. This is the expression for electric field intensity on the surface. So this is also like electric field due to single point charge. So that is why shell is, the charged shell is behaving as if it is a point charge and placed at the center while establishing electric field on the surface and at outside. Next we have to find inside how much is the electric field intensity. So electric field intensity to calculate inside electric field intensity we have to calculate. For that, see this is a charged shell, and inside this is a point where we are going to find out electric field intensity. So through that point we imagine Gaussian surface. Always when we are applying Gauss law, we should imagine one Gaussian enclosure which is called Gaussian surface through the point at where we are willing to find electric field intensity. So through point P we imagine Gaussian surface. So at point P we are going to find electric field intensity, and Gaussian surface radius is small r. smaller, it is really smaller than big R, which is the radius of charged shell. Now, flux formula geometrically is integral E over ds bar, but by Gauss law, flux formula is 1 by epsilon 0 into total charge inside the shell, inside the Gaussian surface. So Gaussian surface is located inside. Inside the Gaussian surface, no charged body is there. Inside this is the Gaussian surface, this is the charged shell. Gaussian surface के बाहर में चार्जड शेल है, Gaussian surface के अंदर में चार्जड शेल ही नहीं है, मतलब क्या चार्जड बॉडी नहीं है, चार्ज नहीं है. That's why Gaussian surface के अंदर में चार्ज 0. So it has Q के स्थान में 0 डालना पड़ा. Then completely flux answer becomes 0. Then flux answer means that both answers if we equate integral E over ds is 0. That means E is equal to 0. In that way, electric field intensity is 0 inside at inside point. So in that way, we understood that electric field inside the shell will not exist. That's why inside the shell no electric field. So no intensity, no field lines. Even field lines we cannot draw because field is not there inside. It is field-free region. It's called field-free region. Next, if we show these three answers graphically by taking electric field intensity on y-axis and the distance r from the center, we can take on x-axis. And from 0 to big R means what? Inside the shell. 0 radius to big R radius, which is the radius of shell. Means what? Inside the shell, electric field is not there. That's why height of the graph is 0. Height of the graph is 0 because height per, we are taking electric field intensity. Electric field intensity is 0 is for height should be 0. At the surface, outside surface, at the surface, outside surface, not inner surface. Outside surface for electric field is maximum, that is sigma by epsilon 0. We got already. And the outside of the surface, if you are going outside exterior point, R is increased, then electric field is decreasing with 1 by R square. We got already. So in that way, this is a graph, how electric field is. Now inside the shell, electric field is 0 we got. Within the material also electric field is 0. Within the material, like this. Material may have some thickness because it is made of metal. So electric field where it is 0, inside 0 electric field, and within the material also electric field is 0 because material is made of conducting material. In the conductor, in static condition, electric field is 0 always. Only on the upper side surface, outer surface, electric field is there, that is sigma by epsilon 0. And at outside, again electric field is there. It is this electric field on the surface is maximum, and outside electric field decreases with the distance. And the direction of electric field is radially outward. So on the surface is there and outside is there. On the surface maximum, outside with the distance it decreases. So that is